The human eye is nature's original optical instrument. It consists of a precise arrangement of organic lenses and sensors evolved to process incoming light. This chart shows the electromagnetic spectrum, and right in the middle is the tiny fraction our retinas can actually detect. Light is simply electromagnetic radiation, waves of electric and magnetic energy moving through space, that falls within a very specific wavelength band, roughly 400 to 750 nanometers. Within that narrow band, light operates on two strict physical rules. First, it travels incredibly fast, nearly 300,000 kilometers per second in a vacuum. Second, it travels in a perfectly straight line. Because light travels in straight lines, the geometry of our eye creates a hard biological limit. If an object is too small or sits too far away, the angle of the light rays entering our pupil is too narrow. Those rays hit too few receptors on the back of the retina for our brain to construct a detailed image. To see past those limits, we have to manipulate the light before it reaches the body. We place carefully shaped glass, mirrors, lenses, and prisms to alter its trajectory. That is the entire premise of ray optics. We engineer the geometry of light to bypass the constraints of human biology. A single curved piece of glass, like a standard magnifying glass, has a hard physical ceiling. Due to its shape, you can only bend the light so much before the image becomes a blurry, distorted mess. To reveal the microscopic world, we stack them. A compound microscope relies on two distinct lenses working in perfect sequence to multiply the magnification. This diagram shows the first step in that sequence. The lens placed closest to the specimen is called the objective. It catches the diverging light rays bouncing off the tiny object and forces them to cross, projecting a magnified, upside-down real image, a projection where the light rays physically converge inside the microscope tube. That upside-down projection then becomes the starting point for the second lens, the eyepiece. This lens sits exactly one focal length away, the precise distance required for its curve to capture those newly organized light rays. The eyepiece treats that first projection as if it were a physical object and magnifies it again. It creates what physicists call a virtual image. This is an optical illusion where the light rays entering your eye appear to diverge from a massive, highly detailed object sitting comfortably in front of you. This graphic displays the underlying math of the system. The total magnification power is simply the magnification of the objective lens multiplied by the magnification of the eyepiece. By compounding the bending power of glass, we force invisible cellular structures to occupy the physical scale required for human vision. Look in the opposite direction and the physics problem reverses. Planets and galaxies are massive, but they sit across such vast distances that only a tiny, faint fraction of their light ever reaches Earth. A refracting telescope uses the exact same two-part architecture as a microscope, an objective lens and an eyepiece, but the geometry is optimized for gathering faint light rather than enlarging tiny objects. This animated diagram illustrates the telescope's objective lens. To catch as many faint parallel light rays as possible, you need a huge piece of glass with a wide aperture or diameter. It also needs a very long focal length, meaning it bends the light gently over a long distance. Those weak parallel rays from deep space hit that massive lens and are funneled down into a single, intensely bright, real image suspended inside the telescope tube. From there, the eyepiece takes over. It takes that highly concentrated point of light and provides angular magnification. It stretches the incoming light rays out so they hit your eye at a wider angle, making the distant star appear drastically closer. This graphic details the telescope's power ratio. You calculate the magnification by taking the long focal length of the massive objective lens divided by the short focal length of the eyepiece. The microscope takes light from a speck and expands it. The telescope scoops up the faint light of an entire galaxy and condenses it to fit neatly through the pupil of a single human eye. Look closely at a dividing cell or peer out at a spiral galaxy millions of light years away, and you're participating in the exact same process. Both instruments rely entirely on the simple geometric rules of refraction, calculating exactly how a wave of light will alter its course when it hits a curved barrier of glass. Today's orbital observatories and medical labs use stacks of multi-component lenses to correct for color distortion and edge blurring. But their architecture still relies on the exact same 17th century mathematical principles of ray tracing. We analyzed the physical properties of light, calculated the geometry of glass, and built optical bridges to the extreme edges of reality.